Please wait. Hello, hello, hello. Am I audible? Okay. So let us start with today's lecture. In last lecture, student, you have studied about transfer function. Okay. How to represent transfer function. So you can represent your transfer function by two forms. Okay. So first one is pole zero form and second one is time constant form, that you know very well. Then what is characteristics equation? So the equation available at the denominator is nothing but your characteristics equation, and you are going to find the roots of that characteristics equation, and that roots are nothing but poles of your system. Whereas these poles, location of poles decide the stability of your system, right? So poles and zeros are may be real, may be complex in nature. Okay. So complex conjugate poles occur in pair. Okay. Then the complex plane, that is nothing but S plane, is used to represent your poles and zeros, right? So depending on location of your poles and zeros, exhibit stability of system. That is nothing but for given transfer function. For given control system, you'll get whether your control system under consideration is stable or unstable. Okay, depending on location of poles and zeros. Okay, so some of these points you have to remember. Now talking about S-plane. So student, you are going to study in today's lecture what is S-plane. Then you are going to study first order system, response of first order system, then some specification, then second order system and their specifications, or you can say in time domain specification, what are the parameters for second order system. All these things you are going to study in today's lecture. So let us start with explain. So are you with me, students? Okay. So this is nothing but your S-plane. Okay, this is nothing but your S-plane. So student, you are supposed to draw this diagram. So on x-axis, I have taken rho, that is nothing but real part. On horizontal axis, I have taken real part, that is rho, denoted by letter rho. Then on y-axis, I have taken imaginary part, that is j omega. So plus j omega minus j omega, plus rho minus rho. Okay, origin is here. Now this is nothing but left half of S-plane. This point, this is S-plane. This point is nothing but left half of S-plane, LHP, left half of S-plane. This point from imaginary axis on the right side, this part is nothing but right hand of right half of S-plane. Okay, so RHP is here, LHP is here, and if your poles are located on left half of S-plane, then only your system is stable. Otherwise, your system is unstable. Okay, so remember this. Now, coming to real axis. So, real axis is varying from 0 to minus infinity on this side, 0 to plus infinity on this side. Okay, got the concept of S-plane? So, draw the S-plane on horizontal axis. This is nothing but real value of your rho, right? Because in S-plane, your variable S, that is related to rho and j omega. So S is equal to rho plus j omega. So rho is nothing but your real axis parameter. Okay. So horizontal axis पे क्या लेंगे हम? X axis पे क्या लेंगे? Rho. So rho is varying from 0 to infinity on this side, right side. Rho is varying from 0 to minus infinity on left half of S-plane. Okay. So on real axis, what is equation for S-plane? S is equal to rho plus J0 at that time, omega is equal to 0. So your equation becomes S is equal to rho plus J0, right? Now, on vertical axis, that is nothing but imaginary axis. Plus j omega on this side, minus j omega on this side. So this is nothing but your imaginary axis. So with this vertical axis, our equation for S plane, S is equal to real term is equal to 0, okay, plus j omega. Now we are going to represent poles by this letter, capital X. So you are going to represent poles available in control system equation, transfer function equation. So poles are denoted by this letter, capital X, and zeros are represented by 0. Okay. So remember these 2 points. S plane, draw the diagram for S plane. Okay. So this is imaginary axis, this is real axis. So your rho is varying from 0 to plus infinity on right side, 0 to minus infinity on left side. This is your positive imaginary axis, and this is nothing but negative imaginary axis. And you can represent your poles by this letter. You can represent your zeros by 0 directly. Okay, understood? Are you with me? चलो आगे चलते हैं. Now talking about first order system. Is the screen visible clearly? Okay. Now give the heading. Students, please give the heading first order system. First order system. So this is the block diagram of first order system. Okay. So you can represent your first order system just by transfer function of process. So this is nothing but your process block. Transfer function of your process block is 1 divided by tau into S. Okay. Then feedback is taken. This is negative feedback, and this is nothing but your unity feedback, because there is no any feedback element present. So at that time, what we are calling that feedback? Unity feedback with negative sign. So you can say negative unity feedback system is available in this block diagram of first order system. So you have to remember, you have to draw the block diagram for first order system. So this is the block diagram of first order system. Okay, only process block is present. When there is no any feedback element, we are calling that system as unity feedback system with negative sign, negative unity feedback system. Okay, now this is nothing but your summing point. R of S is input, E of S is error signal, and C of S is output. Okay, now write the transfer function for this first order system. So how to write transfer function for this first order system? Yes, transfer function for first order system is nothing but you have to take Laplace transform of C of S. It is the ratio of C of S to the R of S. C of S is nothing but Laplace transform of output to the Laplace transform of input. So transfer function for first order system is C of S divided by R of S. So what is the equation for this? Is equal to 1 divided by Ts plus 1. Ts plus 1. So you can derive this equation by your equation, that is nothing but, yes, what is transfer function equation? Gs divided by 1 plus Gs into 1. So put the equation for Gs is equal to 1 divided by tau into S divided by 1 plus tau divided by 1 divided by tau S into 1. Simplify, you'll get this equation. Simplify, you'll get this equation. 1 divided by Ts, that tau S get cancelled. 1 divided by tau S plus 1. So student, please write the transfer function equation for first order system. So this is the transfer function equation for first order system. Transfer function G of S is equal to, in closed loop system, in closed loop system, C of S divided by R of S is equal to So always we are going to start from this equation for first order system. So transfer function for first order system is equal to 1 divided by tau into s plus 1. What is this tau? Tau is nothing but time constant in RC circuit. That you have to remember. Okay. Now, see the step response for this first order system. Apply step input. So what is the equation for step input? R of s is equal to 1 by s. So applied step input over here, R of s is equal to 1 by s is nothing but your step input. So your equation become like this. C of s output is equal to R of s on this side into this term as it is. So R of s into 1 divided by tau s plus 1. For unit step function, R of s is equal to 1 divided by s into 1 divided by tau s plus 1. So this is the response. This is the output. C of s is equal to 1 by s into 1 divided by tau s plus 1. Multiply, you will get 1 divided by tau into s square plus s. Now this is the response for first order system, and you are going to plot the response for first order system, okay, by using psi code. So remember this equation, standard equation, G of s is equal to 1 divided by tau s plus 1 for first order system. So student, you are supposed to write equation for transfer function for first order system is this. Gs is equal to C of s divided by R of s is equal to 1 divided by tau s plus 1. Always you have to remember the equation for transfer function for first order system. Okay. Now test signal, we have applied this input signal is nothing but unit step signal. So what is unit Laplace transform of unit step signal? That is Laplace of 1 is 1 by s. So I have taken 1 by s into 1 divided by tau s plus 1. Simplify, you will get output, and you are going to plot the this response for first order system. You can take any equation over here. You can take any equation in this block. You can take any equation. Okay. For example, G of s is equal to 1 divided by say 5s plus 2, 5s plus 1, like this. So for this transfer function of first order system, you are going to plot the response, that is nothing but CT with respect to time. You are going to plot by using Scilab code. That is our next experiment. Understood? Any doubt? Okay, proceed further. Just wait. So first order system without zeros. Zeros are available in the numerator, whereas poles are available in the denominator. So this is the first order system without zero. Can be represented by following transfer function equation. So transfer function G of s is equal to C of s divided by R of s is equal to 1 divided by tau s plus 1 without zero. This is nothing but your pole. Okay. Denominator में जो भी होता है, we are calling this as pole. Okay. And zeros are present at the numerator. So this is the equation for transfer function of first order system without zero. So you have to remember equation without zeros. Okay. Now given step input is nothing but u of t is equal to 1. That is Laplace transform of 1 is nothing but 1 by s. So for given step input, that is R of s, Laplace of input, R of is equal to R of s is equal to 1 by s. Then what is the response of your system? Then the system output, that is nothing but step response. In this case, we are calling this as step response because input is step input. So you'll get step response. Okay. So then the system output is equal to CT we are going to talk about. So C of S is equal to transfer function equation as it is 1 divided by tau into S plus 1 into RS. What is RS? RS is equal to 1 by S. So put this equation over here. So you will get 1 divided by RS 1 by S into this term as it is tau S plus 1. Now simplify, you will get this equation. You can write this equation like this. Just wait. Just a minute. Yes, is it visible now? So this is nothing but your C of S output. 1 divided by S minus 1 divided by S plus 1 divided by tau. Now this is nothing but in terms of poles. Okay. So what is first pole? First pole is S is equal to 0. Second pole is S is equal to minus 1 by tau. Okay. So if you simplify this, you will get this term. So you can write this term is equal to 1 divided by S minus 1 divided by S plus 1 divided by tau. Okay, in bracket. So you can simplify this equation. You will get poles and zeros. So poles are available at S is equal to 0 and S is equal to 0 and S is equal to minus 1 by T. Okay. Now taking Laplace transform of this equation. Taking Laplace transform of this equation, Laplace inverse transform of this equation, you will get C of T, because this is the equation for C of S. Okay. Take Laplace inverse, you will get C of T. So taking Laplace inverse transform, we have the step response in time domain analysis for first order system. So take Laplace inverse C of T. C of S का Laplace inverse का झाला C of T in time domain आ गए हम, is equal to 1 by S is nothing but 1, and for 1 divided by S plus 1 by tau is nothing but minus e raised to the power minus sign, minus e raised to the power again raised to minus t small t divided by tau. Now this is the Laplace inverse of 1 divided by S plus 1 by tau. So by taking Laplace inverse of C of S, you will get this step response with this equation. Now what is time constant? Suppose if this t is equal to tau. Now listen to me carefully. If this t, small t is equal to tau, time constant. Okay. So what happened? Minus 1 divided by 1. So e raised to the power minus 1. Right? Is nothing but 1 divided by e raised to the power 1. So what is value of e raised to the power 1? Is nothing but 0.37. So your equation become when t is equal to tau. So your step response is Ct tau is equal to 1 minus 1 divided by e raised to the power 1 minus is equal to 0.37. E raised to the power 1 चा काय येत आहे? 0.37 bracket complete. So 1 minus 0.37 is nothing but 0.63. So what is meaning of this 63? 0.63 into 100 करो तो क्या हो गया? 63% हो गया. Okay. So from this figure of time constant, you'll come to know how fast your system is responding. Okay. So in other words, you can say the time constant is the time it takes for the step response to rise to this value, to 0.63, or in percent to rise to 63% of its maximum value. Okay, this is the meaning. So just by putting small t is equal to tau, your step response becomes like this. So C of tau is equal to 1 minus 0.37 is equal to 0.63. So tau is referred to as a time constant of the response for first order system. In other words, same thing is written over here for your ready reference. The time constant is the time it takes for the step response to rise to 63% of its final value or maximum value. Because of this, the time constant is used to measure. What to measure? To measure how fast your system is responding. And the time constant has the unit in seconds. This tau is in seconds. Okay, understood? Got my point? Now see the response for first order system. Now this is the response, step response of first order system in time domain. So you are going to plot this CT by using Scilab code. Okay, for first order system. So on x-axis, time is taken, time is in seconds. On y-axis, output is taken, output is nothing but C of t. Okay, and this is the step response for first order system. So at this point, t is nothing but is equal to tau. And at that time, your system is, output of your system should reach to 63% of its final value. Final value is k. So your output should reach to 63% of its final value when t is equal to tau. That means at this point. Got the meaning of this? So same response you should get by Scilab code. You have to write code for this first order system to find or to plot the response of first order system. Just enter the parameters. Okay, enter the transfer function equation in Scilab, then plot 2D plot. You will get same plot by using Scilab code while saving and executing the code. Okay, now this is what about step response of first order system. Okay, now how to represent? Just take a small example how to represent your first order system in two forms, pole zero and in time constant form. Any doubt up to this? Any doubt, students? No? Chalo, example le lo. Find open loop steady state gain and time constant. First example. Student, you are supposed to write this. Students, please write all these equations for first order system. G of s is equal to 5 divided by 2s plus 1. Second numerical, second transfer function for first order system, G of s is equal to 5 divided by s plus 2. Third equation for transfer function for first order system, G of s is equal to 2 divided by 3s plus 4. So have you written this? लिहिलंय का हे numerical मुलांनो? Now see, starting with first. So take first example, G of s is equal to 5 divided by 2s plus 5. Now this equation is in time constant form, right? This equation is in time constant form, right? K divided by tau s plus 1, right? So what is value of K? K constant, that is what you call steady state gain. K is equal to 5. What is time constant? Time constant tau is nothing but 2. You are going to find open loop steady state gain for this given example. You are going to find time constant for this given example. So observe the first example carefully. Equation for transfer function Gs is equal to 5 divided by 2s plus 1. So this is nothing but your given equation is in time constant form. Okay, in time constant form, this parameter is nothing but k, this one is nothing but your tau, and this is nothing but your open loop steady state gain. So k is equal to 5, right? So write please k is equal to 5 and time constant tau is equal to 2. Finished. Okay, लिहिलं मुलांना? चला आता पुढे जाऊया. Now second, take second example. Transfer function is given for first order system. G of s is equal to 5 divided by s plus 2. Okay, now this transfer function is in pole zero form. Barabar? This is 0, this is pole. So second transfer function equation is in pole zero forms, right? आता आपल्याला ट्रान्सफर करायचं आहे ना पोल झिरो फॉर्म मध्ये आपल्याला कसं पाहिजे 1 डिवाइडेड बाय s प्लस 1 असं पाहिजे आपल्याला ट्रान्सफर फंक्शन राईट पोल झिरो फॉर्म मध्ये सो व्हॉट यू आर गोइंग टू डू यू आर गोइंग टू डिवाइड न्यूमरेटर अँड डिनॉमिनेटर बाय यस बाय 2 1 प्लस फॉर्म मध्ये पाहिजे ना आपल्याला 1 प्लस सम कोएफिशिएंट इनटू s ओके we want our transfer function equation in this form, that is 1 divided by 1 plus some coefficient into s. So for that you have to divide this numerator and denominator by 2. So your equation become 5 divided by 2, 5 divided by 2, yes, divided by s divided by 2 plus 1. Okay, simplify 5 divided by 2 means 2.5, right? 1 divided by 2.5 plus 1. So your equation for transfer function for first order system in terms of poles and zeros, you will get 1 divided by 2.5 divided by 0.5 s plus 1, right? Yes. No, I'm going to show you. Please wait. Take first. Yes, solution is in front of you for first order transfer function equation. This I have explained, right? Again, for your reference, please write. First example, g of s is equal to 5 divided by 2s plus 1. इसके लिए क्या है first order transfer function? K is equal to 5 and tau is equal to 2. This is nothing but time constant form. Now coming to second example, that is g of s is equal to 5 divided by s plus 2. This is the solution. Now this transfer function is in pole zero form, right? So g of s is equal to 5 divided by s plus 2. So you can divide numerator and denominator by 2. You will get 5 divided by 2 divided by s by 2 plus 1. So 5 divided by 2 is nothing but 2.5 divided by 0.5 s plus 1. So this is the transfer function for first order system. Now find k. आपल्याला open loop gain पाहिजे ना, steady state gain. Steady state gain k is equal to 2.5 and what is time constant? Tau is equal to 0.5. So you have calculated steady state gain k is equal to 2.5 and tau is equal to 0.5. Okay, similarly for third example, g of s, take the transfer function. G of s is equal to, yes, 3 divided by 3s plus 4. 3 a की 2 है 2 but 2 divided by 3s plus 4. Again transfer this equation in terms of k divided by tau s plus 1. So what you have to do, you have to divide by 4 numerator and denominator. So the equation becomes g of s is equal to 2 divided by 4 divided by 3 s divided by 4 plus 4 divided by 4 1. So what is 2 by 4? 2 by 4 is equal to 0.5. 3 by 4 is nothing but 0.75 s plus 1. Now find out steady state gain for this example for given transfer function in first order system and find out time constant. So steady state gain for the given example is k is equal to 0.5, k is equal to 0.5 for third example, and tau time constant is equal to 0.75. This is how you are going to solve the small numerical. Got my point? Understood? Any doubt after this? Any doubt after this? No doubt. Okay. Now, so example 1, जो भी था, the following figure gives the measurement of step response of first order system. Find transfer function of this system. Okay. So this is the step response of first order system. You are going to find the transfer function of the system. Reverse way. So what is tau? Tau is, this is nothing but t is equal to tau. So this point is exactly in between point 1 and point 2. So you can write for this t is equal to tau. Tau is equal to 0.15, right? And what is this? This point is exactly, not exactly at center, less than that. So you can write for this 0.45, okay, for approximately 0.45. Now you can write the transfer function equation. Yes, you can write transfer function equation. That is small homework to you. K is equal to 0.45 and tau is equal to 0.15. Write transfer function equation for first order system from the given step response of first order system. You are going to find, you are going to write transfer function of the system. Small homework for you. Please do it. Okay. I will see the answer in next lecture for this example. बघा जमतंय का नाही जमलं तर मी सांगते. Actually, I have given all the parameters. You have to just put into equation the value of tau and the value of a. That's it. Now, some what you call specifications or parameter related to time domain analysis that you are going to study. So first order system transient response analysis. So first parameter is rise time denoted by letter TR. So you should know the definition of rise time. Student, you are supposed to write this. Okay. So rise time is equal to TR. We are going to denote rise time. That is nothing but parameters of transient response of first order system. So please write rise time denoted by letter capital T suffix R. The rise time, this is the symbol of rise time, units in second. Rise time is defined as the time taken for this system or the response, step response to go from 10% to 90% of its maximum value or final value. So student, please write the definition of rise time. The rise time is defined as the time taken for the step response to go from 10% to 90% of its final value or maximum value. Unit for rise time is in second. Equation for rise time is equal to 2.31 tau minus 0.11 tau is equal to 2.2 tau. Write this equation. Then next parameter from transient response, that is settling time denoted by letter capital T suffix S. Now this settling time, yes, again unit is in second, symbol is TS. Settling time is defined as the time taken for the step response to come to within 2% of its maximum or final value of the step response. That is nothing but settling time. Settling means your system is settling down. Okay. So the settling time is nothing but, it is defined as the settling time to be the time taken for the step response to come to within 2% of the final value of the step response. So TS is equal to 4 into tau. This is the equation. 4 TS is equal to 4 into tau for first order system. Now, from this plot, let us see. On this axis, x-axis, I have taken time in second. On this axis, I have taken output in time domain. That is nothing but output is denoted by letter C of t in time domain. So this is the response of in time domain analysis for first order system. So this is the response, initial slope. Okay. This is the response, initial slope. Initial slope is nothing but A. Initial slope is nothing but 1 divided by time constant. So for this time constant, one time constant is equal to 1 by tau. 1 by tau is nothing but A. Slope of this line is A. Okay. So initial slope is equal to 1 divided by time constant is equal to A. So what is tau? Tau is equal to 1 divided by A. So tau is equal to 1 divided by A. A is nothing but slope of this line. Okay. Now, according to rise time, this is nothing but T is equal to tau. Okay. So when your time is equal to tau, T is equal to tau, your response should be equal to 63% of its final value. Final value is equal to 1. Okay, that means output is equal to 1. So 63% of final value means here at this point above 6, above 0.6, sorry. So here is nothing but 0.63. So this point, if you have taken the projection, at T is equal to tau, tau is equal to 1 by A, your system response should reach to 63% of its final value. 63% at this point of its final value at T, and that is nothing but one time constant. That T is nothing but one time constant. So I have taken 1 by A. Second time constant, 2 by A. Third time constant, 3 by A, 4 by A, 5 by A, like this. Okay. Now talking about rise time. So according to definition of rise time, yes, your system response for first order system should reach from 10% to 90% of its maximum value or final value. Final value is 1. So 10% is here. 0.1 is nothing but 10%. 90% is nothing but 0.9. 0.9 into 100, 90%. Okay. So 10% is here. 90% is here. So take the projection like this on this response. So when your system response is rising from 10% of its final value to 90% of its final value, that is nothing but rise time. From this point to this point is nothing but rise time. बघा, इथून आपण घेतलंय student from 10% of maximum, and when your response is reaching to 90% of maximum, okay, taking the projection on x-axis. Now this much is nothing but your rise time. Okay, got my point? When system response, step response is rising from 10% to 90% of its final value. Time taken for your response to reach from 10% to 90% of final value is nothing but rise time. Okay, according to definition, just you have written the definition. I have shown you what is rise time in the first order system response. Now, settling time. What is settling time? When your final response is reaches to 2% of its final value. So this is nothing but 2% of final means just less than 2%. So this is the time taken for your system in first order system. That is nothing but from this point to this point. Okay. So this is the time. Okay. So from this point, from this point, this is nothing but your settling time. Okay. Got the definition and parameters, or you can say specifications in time response, in time domain analysis for first order system. So you have to remember rise time, you have to remember settling time, equation for rise time, equation for settling time, along with definition of rise time and settling time. Okay, now any doubt up to this? Now coming to second order system. So student, you have studied now First order system. Now I'm going to talk about second order system. So give the heading second order system. Similar to first order system, you are going to plot the response, step response for second order system. You have to study all the parameter related to steady state response and transient response of second order system. So students, give the heading second order system. So second order system exhibit a wide range of responses which must be analyzed and described. Whereas for a first order system, varying a single parameter changes the speed of response. That is nothing but tau. Changes in the parameter of a second order system can change the form of the response. Okay. For example, a second order system can display characteristics much like a first order system up to some extent, or depending on component values, display damped or pure oscillations for its transient response. Now in second order system, students, we are going to use the equation for transfer function for process, and in that equation two what you call two components, two parameters are very important. That is nothing but omega n and zeta. What is omega n? Omega n is nothing but natural frequency, and zeta is nothing but damping factor. Okay, so let us see the equation in terms of omega n and zeta. So a general second order system is characterized by the following transfer function. So you have to remember this equation for second order system. Generally, the transfer function equation for second order system is characterized by this equation. G of s is transfer function is equal to b divided by s square plus as plus b. Okay. Now, you can rewrite the above transfer function in terms of closed loop transfer function for second order system. So closed loop transfer function for that is nothing but again denoted by letter G of s. Closed loop transfer function for second order system is equal to omega n square divided by s square plus 2 zeta into omega n into s plus omega n square. Student, please write this equation. So this is very important equation. Please write this equation. This is the closed loop transfer function for second order system. And we are going to use this equation. पुढच्या सगळ्या स्लाइड मध्ये आपण हे इक्वेशन यूज करणार आहोत. So this is the closed loop transfer function for second order system. Please write in your notebook. G of s, give the heading second order system. This is the transfer function for closed loop. This is closed loop transfer function for second order system. Please write this equation is very important. G of s is equal to omega n square divided by s square plus 2 zeta omega s plus omega n square. What is omega n? Please write omega n is equal to natural frequency, and this zeta is nothing but damping factor. So depending on these two values, zeta and omega n, you'll come to know there are four types of second order system depending on zeta. By keeping natural frequency term constant, omega n is fixed frequency. Natural frequency is fixed, but zeta is varying. So depending on value of zeta, you will get four types of systems that you are going to study in detail. Okay. Are you with me, students? So what is omega n? Omega n is natural frequency, referred to as undamped natural frequency. One more frequency you are going to come across, that is damped frequency. We'll see later on while deriving the equation for all these parameters or specifications in second order system. Okay, so now just remember what is omega n. Omega n is undamped natural frequency of the second order system, which is the frequency of oscillations of the system without damping. Undamped means without damping. Okay, and what is zeta? Is denoted by this letter Zeta is referred to as the damping ratio or damping factor. In some references, it is called as damping factor. Okay, damping ratio of the second order system, zeta, which is a measure of the degree of resistance to change in the system output. So these two definitions you have to remember. What is natural frequency, omega n, and what is zeta, that is damping factor. Okay, now poles for second order system you will get in terms of like this. You know the transfer function equation. From that transfer function equation you have to find poles, so you'll get equation for poles for second order system in terms of omega n and zeta is minus omega n zeta plus omega n under root of zeta square minus 1. Second pole is minus omega n zeta minus omega n under root zeta square minus 1. So these are the poles. Okay, poles are complex if zeta is greater than 1. Yes, I agree with this. If zeta is greater than 1, poles are complex in nature. आता आहे का complexity poles मध्ये? Now observe these two equations carefully. These are two poles of your characteristics equation. Characteristics equation is nothing but that is available in the transfer function equation. Denominator of your transfer function is nothing but equation for characteristics, that is we are calling as characteristics equation. You are going to find the poles of that characteristics equation, and if your system is second order system, these are the equations for poles. If the value of zeta is greater than 1, poles are complex in nature, complex conjugate. Okay, any doubt up to this? Students, any doubt? No? Okay, now depending on the value of zeta, that is damping factor. So according to the value of zeta, the second order system can be set into one of the four categories. Okay, if damping factor zeta is greater than 1, the system is overdamped. And when the system has two real distinct poles, zeta is greater than 1. Then second category is underdamped, when zeta is less than 1, or when zeta is lying between 0 to 1, less than 1. When the system has two complex conjugate pole, in this case, in underdamped system. Okay. Undamped, third category, undamped. At that time, zeta is equal to 0. And at that time, the system has two imaginary poles. Last category, zeta is equal to 1. We are calling that as critically damped system. At that time, the system has two real but equal poles when zeta is equal to 1. So student, you have to remember all these four categories for second order system. So according to the value of zeta, you will get overdamped system, you will get underdamped system, you will get undamped and critically damped system. Again, I am repeating, when zeta is equal to 0, the system is undamped. When zeta is equal to 1, the system is critically damped. When zeta is less than 1, the system is underdamped. When zeta is greater than 1, the system is overdamped. Understood? Now for all this category, you are going to derive the equation for peak time, settling time, then resonant peak and omega d, resonant frequency. Okay, you are going to derive the equation. We'll see one by one. Thank you students for attending. If you are having any doubt, please ask me here itself. Now we are going to start the time domain analysis for second order system. इथपर्यंत समजलंय what is second order system, what is equation, how you are going to represent second order system depending on assuming here omega n natural frequency is constant, but the value of zeta is changing. When zeta is changing, you will get four categories of what you call second order system. So these second order systems are having four categories depending on value of zeta. When zeta is equal to 0, when zeta is equal to 1, when zeta is less than 1, when zeta is greater than 1. So all 4 categories you are going to study in detail. In next lecture, we'll see all these things. Thank you, students. Thank you all. Please write your roll number in chat box with understanding. Then you are free to move.